All right, today we are going to talk about parent functions and transformations. This is lesson 1.5. I will let you know it would be wise to have a piece of paper out as we cover these because a sketch of these different graphs may become very useful in the following problems and for the homework. All right, let's get started. So these are our first four parent functions. The first one is a constant function. This is one where it looks like y equals c or f of x equals c. And when c equals 0, when it's right on this line right here, that is called the zero function. Okay, so a constant function is simply a straight horizontal line. Then we have the identity function. It's called the identity function because whatever you put in is the exact same thing you get out. Now you might recognize this as a regular line, and it is this line that we modify when we have the form y equals mx plus b. If you make m be 1 and b be 0, you will have the identity function. And we'll explain what these are in just a little bit. But the identity function is in the form f of x equals x, or y equals x. Then you have the quadratic function. We've worked with this together for quite a while. The quadratic function is in the form f of x equals x squared. And you're going to have this U-shaped. You'll notice it goes through 1, negative 1, 1, 1, 1, and 0, 0. These are places where it's useful to know where it passes through so you can sketch. The other thing is it passes through negative 2, 4, and 2, 4. Those are the points I tend to have that I move as we transform this graph. And then we have the cubic function. The cubic function is in the form f of x equals x cubed. And it passes through 0, 0, 1, 1, and negative 1, negative 1. These are the points I will be drawing as we sketch these graphs. Next we have the square root function. Now notice this is only the positive version and it ends at 0. So it's 0, 0, 1, 1, and then you'd have 4, 2. This is the quadratic equation tipped on its side. And it's only the positive because if we had the one that goes like this, then it would no longer be a function because it wouldn't pass the vertical line test. This is in the form f of x equals square root x. And then we have the reciprocal function. The reciprocal function is in the form f of x equals 1 over x. And this is the one I sketched a couple days ago. Just these curves that stay in quadrant 1 and quadrant 3. Now the points that I look at is this 1, 1 and negative 1, negative 1. Because as we are transforming this, we're going to watch where these points move so that we can draw our graph correctly. All right, the absolute value function, another parent function. Okay, you will see it in this form, but you probably have not thought about it. It is really this system of equations that we're graphing. So that if x is like negative 2, so if it's here at negative 2, then we graph the negative of negative 2, the opposite of negative 2, which is positive 2, and that's where we get this point. So really the V-shaped is created by these two lines. And it changes negatives to positives, 0 stays 0, and positives stay positive. The greatest integer function. Now I know this function as the floor function. Okay, the floor function is basically the integer just underneath your fraction. For example, if I have 1/3, okay, the integer, the full integer that's beneath that. So if I'm here at 1/3, okay, think of 1/3 in y, right here. The biggest integer, you'd come down to 0, okay? I like thinking about in y for the floor function. But basically, as x goes along, it stays at 1 until it hits 2, and then it jumps to 2, and then it jumps to 3, and then jumps to 4, then jumps to 5. In the same way, the negatives work. So this is where it can get a little confusing on the floor function. Negative 1.5 is right here, but the greatest integer underneath it, okay, the integer that's fully covered already, fully filled up. So you can think of yourself here. We haven't fully made it to negative 1 yet, so we fall back to negative 2. And then, of course, if you're at an integer, you just stay at that integer. One way you may see me write this is like this. That's how I write the floor function. There's another function that's very similar called the ceiling function, and it's like this, and it simply means that if you have a piece of an integer, everything goes up. So this one, it all goes down, that one, it all goes up. When you get into computer programming, these two functions are very common. So that's the main place where I actually learned about the floor function and the ceiling function. And in your book, it will say that this is also known as the floor function. All right, so I left the whole example here so that you could see what we needed to do. But we are going to do this using the absolute value parent graph. They're doing this for the square root function. Okay, so their domain is going to be unique and all these different things are going to work. All right, so for our domain, okay, domain, we are talking about absolute value x. Well, that is defined everywhere, and so I'm going to go from negative infinity to infinity. If you're having trouble remembering that, review your interval notation and also make sure you have arrows on the ends of your graphs so you can see that they continue even though on the graph they appear to end. Next, range. Okay, the range is going to go from 0, and I can equal 0, and it will continue all the way up to infinity. Remember, these are the y values. Intercepts. Okay, the only place where it touches or crosses the x-axis is at 0, so x equals 0, and the only place it crosses the y-axis is at y equals 0. So these are my two intercepts. Now up above you can see that they wrote them as a point, 0, 0, and that's mainly because, come on, let me do my comma, there. That's because there was only one intercept. If you had intercepts for the x and the y, then you'd have to list them separately. Okay, so next I need to deal with the symmetry. Oof, my pen just freaked out a little bit there. All right, symmetry. Now I'm going to draw this here so that you can see it. Okay, the square root or the absolute value function does like this. And it keeps going. Those arrows are useful. This one is symmetric about the y-axis. Okay, now you guys will have to decide if it's even or odd. I'm not going to tell you that in this video. But figure out, is this an even function or an odd function if it's symmetric about the y-axis? All right. Next, continuity. Okay? Continuous. Okay, listen, pen. You gotta let me write and not fill in everything. Okay, this is continuous everywhere because I can draw this entire graph without picking up my pen. All right. End behavior, okay? So the end behavior as the limit, so we're going to write the limit of f of x as x goes to infinity. That is going to be infinity. Okay, that is the right-hand behavior. We also need the left-hand behavior. Equals infinity as x goes to negative infinity. Okay? These are both very important. You need to have left and right. For them, their graph begun at x equals 0. So they had a dead end as their beginning. Okay? Intervals on which the graph is increasing and decreasing. Okay? It is decreasing in this part and increasing in this part. So from negative infinity to 0, and not at 0 because 0 is that point where it turned. I can't say if that's decreasing or increasing. The slope at that point is weird because I could draw it this way and I could draw it this way. So I can't say that 0 is increasing or decreasing, but this part is decreasing. Man. All right. And for the other part, let's see, from 0 to infinity, it's increasing. I am so sorry, my pen is really acting funny. All right, let's move to the next page. So we can have translations when it's plus k. We always think of plus k. If k is positive, it's going to move it up. If k is negative, it's going to move our graph down. Also, horizontal translations are inside the function. Notice this one is outside the function. This one is inside the function. Okay, the inside the function, if this is a minus something, it's moving the whole function over h. Okay, if it's a plus something, it actually moves it toward the negative. I always think of it as whatever's with the x, it works opposite. When it's inside with the x, it works the opposite direction as when it's outside. Outside is normal. When it goes inside, everything's backwards. So let's try graphing these functions. Okay, so I'm going to start with the parent function, and the parent function here is x cubed. So that's a dot here, and a dot at 1, 1, and a dot at negative 1, negative 1. And then I have this little curve that goes in between like this. Okay, now this translation lets you know that I went down 5 units. So I'm going to come down here and say this is negative 5. And then here is negative 4. And here is negative 6. So this point is going to come down 5 units and go here. This point will come down 5 units and be here. And this point will also come down 5 units and be here. And then my graph stays the same shape. Come on, there we go. Okay? Now this inside part. Again, notice the cubed on the x. This is a horizontal translation. So I'm going to start with my original, which is here at 0, 1, 1, and negative 1, negative 1. And it does this and this. Now, this is opposite land because it's inside with the x. That means I'm going to move plus 3 horizontal units. 1, 2, 3. I'm going to make a fourth mark. So this 0, 0 is going to go 1, 2, 3 places and end up here. Then I still have this diagonal that I keep. And here is my new graph. Okay, go ahead and try this one. Notice you're going to have a horizontal shift of negative 2 and a vertical shift of positive 4. Go ahead and try that one. It's worth trying to figure out. All right, so reflection across the x-axis is this negative 1 in front of the function. If it's in front of the function, it's just going to flip it across the x-axis. If it's inside the function, okay, then it flips it across the y-axis. So let's look at how this is related. Well, remember this graph, I'm going to draw it right here. It does something that looks like this. Okay, where this and this are 1, 1, and 1, negative 1. Okay, so if I'm looking at this graph and this one, the first thing I notice is that my vertical line, my horizontal line has been moved down by 2. And you can see it's been flipped this way. It left this quadrant, went to that quadrant. So to write this function, I would get g of x equals, and then to flip it, I need the negative 1 over x. And then I need to do a vertical shift of negative 2, minus 2. That will bring everything down. Now how about this one? Well, the first thing I notice is I've got a horizontal shift to here, where this line is in the wrong place. I also have these curves in the wrong place. So for this one, g of x is going to equal negative 1 over x. But now to do the horizontal shift, I need to put this number in with x. And it's 1, 2, 3, 4 in the negative direction. So that's minus negative 4, which will give me negative 1 over x plus 4. All right, vertical dilations. This is fairly simple, kind of, if you think about it. So basically what we're doing is we are taking, using this value in front of a function, and moving a point vertically up if it's positive, or the point vertically down if it's negative. And that makes these appear wider or narrower. But what we're doing is we're actually shifting the points up or down. Okay? Now, if the number is in with x, then it's going to change it horizontally, just like we had horizontal shifts when it was added or subtracted to x inside the function. So this will move a point from here in if it's bigger than 1, and out if it's smaller than 1. All right, so let's work with these two functions real quick. So this one is my greatest integer function, and minus 4. So using my graph here, I have a dot at 0 and over to 1 where it's a circle, a dot at 1 and over to 2 where it's a circle, a dot at 2 over to 3 where it's a circle. Okay, this is my function. Now, I am going to change my pen color here so that I can draw my other function. This function is shifted negative 4. That means this point has got to go 1, 2, 3, 4 over. Sorry, not in the horizontal, not this direction. In the vertical direction. 1, 2, 3, 4. So here's my point, and I go over and draw a circle. And then here's my point, go over and draw a circle. Point over, point over. Okay? That's how that shift worked. Now this shift, this is going to be a reciprocal shift. And notice, I'm going to rewrite this. This is 15 times 1 over x plus 3. So this is going to make everything narrower. It's going to make it smaller. And so in our case, it's going to keep it closer to the axes. This is our parent function, and we're going to shift up 3. So normally, I would have this function. Okay? But now, let me change my pen color again so that you can see it. Pen color, back to red. So now we have to shift this up vertically 3 places. 1, 2, 3. This is my new asymptote. I am trying to do dots there. And I'm going to stay very, very close to my asymptotes here. Like so. All right, I am going to graph one of these, and you guys can graph the other one. I am actually going to graph this one, but I want you to see how we graph a system of equations. So if it's less than 0, I'm going to follow this line. Well, at 0, this is going to be at -5. 1, 2, 3, 4, 5. So at 0, this is defined. And then my slope is positive. So I'm going to go down like this so that as I go here to here, I'm going up 1 each time. Okay? Then I have x cubed between 0 and 2. So here's 1, 2. Now the cubed function, I'm not equal here, but it goes at 0 and then 1, 1. And then if I put 2 in there, 2 cubed is 8. 1, 2, 3, 4, 5, 6, 7, 8. And it's equal to here with a dot. So now I just need to connect my graph. Okay? And then it's 2 over x if x is greater than 2. So that is this curve. If you guys can think about it this way, it goes like this. So then we make a circle here at 2 and we simply trace it down this way. That's how you do a piecewise function. All right, transformations of the absolute value. If you have your entire function in the absolute value, then that whole function comes up top. So all of this that's underneath the x-axis just flips up top. And if you have the absolute value around your x inside the function, whatever is on the right side of the y-axis will be repeated, mirrored on the left side. Okay? So, for these graphs, we need to find these two things. If I'm going to have the absolute value on the outside, that means anything below gets flipped up to the top. So I'm going to end up with this. And for this one, anything below gets flipped up top. So then I get my circle here and it goes to a dot, a circle here and it goes to a dot, and a circle here and it goes to a dot, and a circle here and it goes to a dot. Now let me change my pen color and we'll graph the other possibility. All right, so if I have this inside, then the right gets repeated, the right side of the axis gets repeated on the other. So here's my thing, and it actually goes, let's see, it goes right here. This is what I get. Okay? And here, it gets repeated across. So this goes like, the positive side gets repeated on the negative. Open, solid, open, solid, open, solid. So it's just mirror image. So the way this was going up like this gets mirrored across the y-axis. All right, your homework is on Alex. Go ahead and get started. Don't forget to copy down the parent functions. Have a great day.